Hey guys, have you ever looked up at the night sky and wondered what would happen if you just kept going? Like really kept going, past the stars, past the galaxies, past everything you can see with your eyes, or even with the best telescopes humans have ever built? Would you eventually hit a wall, like the end of a video game map, or would you just keep drifting forever into some kind of cosmic endlessness? In this video, we're going to take that journey together, traveling slowly and calmly all the way to the edge of the observable universe, while you relax, breathe deeply, and maybe drift off to sleep, while your subconscious mind wanders along with me into the deepest and strangest mysteries of the cosmos. Because honestly, the edge of the universe is both one of the most fascinating and one of the most confusing ideas in astronomy. And it's exactly the kind of thing that keeps you awake at night if you're not careful. So let's turn it into something that helps you fall asleep instead. Now, before we start blasting off like astronauts in some over-dramatic movie scene, let's take a moment to set the mood. You're lying back, your eyes are closed, and you can feel the weight of the day starting to lift. Imagine the Earth beneath you, a whole planet spinning quietly in the dark, and above it, the endless stars scattered like dust across black velvet. It looks calm, doesn't it? But what we're about to do is zoom out in a way your mind can follow, step by step, until the stars you see now will become just tiny points in a much bigger picture, and then tinier still until you can barely believe what you're looking at. But let's ask the first genuine question. What does it even mean to say edge of the universe? Because edges usually imply something solid like the edge of your table or the edge of your bed that you always manage to stub your toe on. The universe isn't like that, and unfortunately there's no big glowing sign floating in space that says, "Congratulations, you've reached the end." If only it were that simple. Instead, the edge of the universe is really about light. It's about how far light has had time to travel since the beginning of everything, since the Big Bang. Light is fast, the fastest thing we know, but it's not instant, and the universe is old but not infinite in age, about 13.8 billion years, give or take. So what we call the edge is just the farthest distance from which light has had time to reach us since then. And here's the fun twist. Because the universe has been expanding the whole time, that distance isn't 13.8 billion light years, it's much larger. More like 46 billion light years in every direction. That's the radius of our observable universe. So when I say we're going to the edge, I don't mean we're leaving the whole universe. I mean we're heading to the horizon of what can be seen, like sailors on an ocean, sailing toward the line where the sky meets the sea, except in our case the horizon isn't an illusion of perspective. It's the actual limit of light and time. Let's start small though. Because right now you're still standing on Earth, which feels enormous from your perspective, even though we know it's basically a pebble floating in space. And the first thing you'll notice as we rise higher is that Earth becomes a sphere, then a blue marble, then just another planet orbiting the Sun. Our little solar system is comforting, with its family of planets circling like clockwork, but compared to what's beyond, it's tiny to the point of being laughable. Think about it. If the observable universe was shrunk down to the size of Earth, our solar system wouldn't even be visible under a microscope. Not even Jupiter with its great red spot. Not even Saturn with those famous rings. That's how outrageously small our neighborhood really is. And yet to us, it feels infinite most of the time. So we start rising, past Earth, past the Moon, past the orbit of Mars and the asteroid belt, past Jupiter with its giant storms and Saturn with its icy rings, until we're outside the solar system completely. And here's the funny thing. From this vantage point, the Sun itself starts to look like just another star, nothing special at all, even though it's literally the reason you exist. You've just met humility, served up in cosmic proportions. As we move farther out, stars begin to cluster, and the Milky Way galaxy comes into focus. Imagine looking at billions of suns arranged in spiraling arms, glowing in shades of indigo and saffron, connected by rivers of dust and gas. Our entire planet, our entire species, every story ever told, All of it is tucked into just one of these spiral arms. It's like discovering your entire life fits inside a single neighborhood on the edge of a massive glowing city. And yet, as vast as the Milky Way is, it's still just one galaxy among billions. We're part of a local group, which sounds like the name of a boring Facebook community group, but in reality is a small gathering of galaxies bound by gravity. The Milky Way and Andromeda are the two big players, and they're slowly drifting together in a cosmic slow dance that will eventually end in a colossal galactic collision. Don't worry though, it'll happen billions of years from now, so you can still make your morning coffee without stressing about it. Now let's zoom out even more. Past the local group, past the Virgo cluster, past superclusters of galaxies that sprawl across space like cosmic cities, until the pattern reveals itself. The universe is not random, not just scattered dots of light, but a web, a structure. Galaxies align in filaments, strands of light stretched across unimaginable distances, with dark voids in between, like holes in cosmic fabric. It looks less like empty space, and more like the neurons in a brain so vast it would take light billions of years to cross. And here's where the idea of edge becomes really strange. Because if you keep going, if you zoom out far enough, eventually you see not individual galaxies, not clusters or filaments, but the faint afterglow of the Big Bang itself. This faint glow is called the cosmic microwave background, and it's basically the universe's baby picture, frozen from when it was just a few 100,000 years old. It's a field of faint, uniform radiation that fills every corner of the sky, no matter where you look. Beyond that, we simply cannot see, not because nothing exists, but because light hasn't had time to get here. It's like waiting for mail from a distant friend who hasn't even finished writing the letter yet. The information just hasn't arrived. So when we talk about traveling to the edge of the universe, what we really mean is traveling to the edge of what we can observe. To stand at that edge would be to look back in time itself, to see galaxies as they were billions of years ago, to see the faint glow of creation stretching across the horizon, and to realize that beyond it, mystery continues. But of course, the real question is, if you could actually get there, if you could somehow stand on the horizon of the observable universe, what would you see? Would you see nothing but black, or would you see other universes budding off like bubbles, hidden from our view but just as real as ours? Would you find the universe looping back on itself so that the farther you went, the closer you came to home? Or would you find infinity stretching forever with no edge at all? The truth is, no one knows, and maybe no one ever will. But that's the beauty of the edge of the universe. It's not just a place in space, it's a place in thought. It's where science meets imagination, where physics meets philosophy, where your mind can wander endlessly and maybe even drift into sleep. So close your eyes a little heavier now. Imagine yourself floating higher, drifting beyond the galaxies, beyond the clusters, beyond the filaments, until you're standing at the edge of the observable universe, gazing at the faint afterglow of everything that ever was, and just beyond endless possibility, the sun shrinks behind us until it is nothing more than another star, one anonymous speck in the crowded spiral of the Milky Way. From the Earth's surface, it feels impossibly large, a furnace so bright you cannot look at it directly. Yet here in the wider galaxy, it blends into the background like a drop of water lost in an ocean. Our home star is classified as a G-type main sequence star, not particularly rare, not particularly special, the cosmic equivalent of someone describing their favorite meal as bread. About 1 in 10 stars in the Milky Way are roughly similar, so statistically speaking, the Sun is not winning any awards for uniqueness. It just happens to be ours, and that alone is enough for us to write poetry about it, and fear the day it eventually swells into a red giant and cooks the inner planets like unfortunate marshmallows left too long in a fire. As we continue rising outward, the structure of the galaxy sharpens into view. You see the spiral arms laid out in arcs of light, 4 main arms with numerous spurs and bridges between them, each containing billions of stars. Dust lanes, thick with gas and microscopic grains of carbon and silicate, snake across those arms, blocking the light behind them and giving the Milky Way its mottled appearance. The central bulge glows with dense stars orbiting around a supermassive black hole, Sagittarius A, which sits at roughly 4 million times the mass of our Sun. It's a cosmic heavyweight, but still modest compared to black holes in other galaxies that reach billions of solar masses. You might imagine it as the gravitational anchor holding everything together, but in truth, the majority of the Milky Way's structure is shaped not by what we can see, but by dark matter, that mysterious invisible substance making up roughly 85% of the galaxy's mass. Without it, the stars in the outer arms would simply spin away into intergalactic space. With it, the galaxy maintains cohesion for billions of years. Drifting farther, the Milky Way itself becomes small enough to grasp in a glance. A disk about 100,000 light-years across, thin as a coin in proportion, holding maybe 200 to 400 billion stars. The numbers are so absurd they stop meaning anything concrete, and yet here they are, each one a potential home for planets, some rocky, some gaseous, some frozen, some too strange for us to even imagine. Our galaxy is just one island in a universe filled with them. And soon even this luminous disk fades to a point in the dark ocean around it. Close by floats Andromeda, M31, a spiral galaxy even larger than the Milky Way. It contains perhaps 1 trillion stars and shines brightly enough that under a dark sky you can see it with the naked eye, appearing as a faint smudge in the constellation Andromeda. Astronomers have already charted its motion and know it is hurtling toward us at about 110 kilometers per second. That might sound fast, but on galactic scales it is the slowest of dances. In about 4.5 billion years, the Milky Way and Andromeda will collide and merge, tearing their spiral arms apart in tidal interactions before eventually settling into an elliptical galaxy, unimaginatively nicknamed Milkdromeda by astronomers who clearly did not spend enough time on branding. You won't need to worry about it personally, but it is a reminder that nothing in the universe is permanent, not even galaxies that feel impossibly eternal to us now. Together, the Milky Way, Andromeda, and a few dozen smaller galaxies form what is known as the Local Group. Spanning about 10 million light-years across, it is not very large by cosmic standards. The dwarf galaxies orbiting around the two big spirals are irregular in shape, some resembling cotton balls of stars barely held together by gravity, others stretched thin by tidal forces. The large and small Magellanic Clouds, visible from the southern hemisphere, are among the brighter examples. They are technically satellites of the Milky Way, dragged around in. From here, the Local Group is just a grain of rice in a giant bowl. Look beyond and you find yourself inside the Virgo supercluster, a sprawling region 110 million light-years across containing thousands of galaxies grouped into clusters. Our Local Group is a minor member on the outskirts, not even at the center stage, which is dominated by the Virgo cluster itself, with over 1,000 galaxies orbiting a common gravitational well. Galaxies in clusters don't live quiet lives. They collide more often, their stars are ripped out to form faint bridges and streams, and many spirals are stripped into dull ellipticals, losing their gas and their ability to form new stars. Astronomers call these red and dead, which is somehow both poetic and depressing. But the Virgo supercluster itself is not the final step up. In the 1980s, astronomers realized that superclusters are not isolated. They link into even grander formations, cosmic filaments stretching hundreds of millions of light-years, connecting clusters like beads on threads. These filaments weave into the cosmic web, the largest scale structure of the universe. If you could look at it from outside, you would see bright strands of galaxies interconnected, forming a kind of three-dimensional spiderweb, with enormous voids in between where almost nothing exists. Some of those voids are hundreds of millions of light-years across, cosmic deserts where a spaceship could travel forever and never pass a star. Our Virgo supercluster is itself just a lobe of an even larger structure called the Laniakea supercluster. The name means immense heaven in Hawaiian, and it covers over 500 million light-years, encompassing about 100,000 galaxies. Within it, gravitational flows direct galaxies like rivers channeling water, and our Milky Way happens to be drifting along one of these rivers toward the so-called Great Attractor, a region of immense gravity about 150 million light-years away. No one is quite sure what the Great Attractor actually is, but it bends the motion of thousands of galaxies, pulling them in like an invisible sinkhole. In astronomy, "we don't know" is an answer you hear a lot, usually followed by, "but we're working on it," which is both comforting and frustrating at the same time. Zoom farther still, and the details begin to blur. The cosmic web itself becomes visible. Immense filaments of galaxies threading across the void, knots at intersections where clusters converge, and emptiness stretching between like black oceans. It's not just beautiful, it's also evidence of the early universe's growth. The pattern we see now is an echo of tiny quantum fluctuations magnified by cosmic inflation, those fractions of a second after the Big Bang when the universe expanded faster than the speed of light. Those ripples were frozen into the density of matter and eventually grew into the filaments and voids we see today. In a sense, the shape of the entire cosmos was written in the smallest irregularities, amplified to scales of billions of light years. This is the point where human language begins to break down. 100,000 light years is one number, 10 million another, 100 million another still. But eventually the magnitudes stack so high they stop meaning much. It is like trying to imagine the number of grains of sand on Earth, not just on beaches, but deserts, riverbeds, the ocean floor, everywhere. You can say the number, but you can't truly hold it in your mind. And that is what standing here feels like, staring at the cosmic web, knowing you are looking at scales so huge your brain is only pretending to keep up. Now, what about the so-called edge? You've already passed clusters, superclusters, filaments, and voids, but there is still farther to go. Eventually you reach the cosmological horizon, the limit of the observable universe. This is set not by a wall, not by any kind of barrier, but by the finite speed of light and the finite age of the universe. The cosmos is about 13.8 billion years old, which means light has had 13.8 billion years to travel. You might think that sets the edge at 13.8 billion light years, but because the universe has been expanding all the while, the actual distance to that horizon is about 46 billion light years. The light you are seeing has been on the road for nearly 14 billion years, but the source itself is now far, far away. What you find at this horizon is not galaxies or stars, but the cosmic microwave background, the faint afterglow of the Big Bang itself. Discovered accidentally in 1965 by Penzias and Wilson, who at first thought the signal was caused by pigeon droppings in their antenna, the microwave background is uniform radiation filling all of space. It comes from the time when the universe cooled enough for electrons and protons to combine into atoms, about 380,000 years after the Big Bang. Before that, the universe was a hot plasma, opaque to light, scattering photons like fog. Once atoms formed, light could travel freely, and that ancient light has been traveling ever since. Today, we detect it as microwaves stretched by the expansion of the universe into wavelengths about a millimeter long. If your eyes could see microwaves, the entire sky would glow faintly, evenly, in every direction. At first, it seems uniform, but detailed measurements reveal tiny variations, 1 part in 100,000. Those tiny anisotropies are the seeds of structure, the fingerprints of the early universe that grew into galaxies, clusters, and filaments. Without them, there would be no stars, no planets, no you. The next time you feel ordinary, remember you are literally a product of tiny wrinkles in the temperature of the cosmos when it was less than 1 million years old. Humbling, isn't it? And here you find yourself asking the question again, what lies beyond? Beyond this horizon there is certainly more universe, but we cannot see it. Light simply hasn't had time to reach us. It is not that those regions don't exist, it's just that they are causally disconnected from us, hidden by time itself. The observable universe is like a bubble of visibility around us, expanding as time passes, revealing more of what was always there. We are trapped inside our bubble, but the bubble grows every year as new light finally arrives from farther away. It is not infinite access, but it is infinite patience. Of course, cosmologists cannot resist speculating. Maybe the universe is infinite, stretching forever in every direction, with no boundary and no edge. Maybe what we see is just one patch, one observable region in an endless expanse. Or maybe the universe is finite but unbounded, curved like the surface of a sphere. If that is the case, traveling straight in one direction might eventually bring you back to where you started, like circumnavigating the globe, only on scales billions of times greater. And then there is the multiverse idea, the possibility that inflation produced many universes, each with different laws of physics. Some collapsing instantly, some expanding forever, some empty, some teeming with galaxies. Our observable universe would be just one bubble among countless others. You cannot see those possibilities from here, but you can imagine them. And perhaps imagination is the most powerful telescope we have at the moment. So here we stand, 46 billion light years out, staring not into the present, but into the ancient glow of creation itself. And you realize the so-called edge of the universe is not really the end of anything. It is the limit of what light can tell us, the boundary between knowledge and speculation. Beyond it, reality continues, indifferent to whether you can see it or not. And maybe that is the ultimate lesson here. The universe is larger than your comprehension, older than your species, stranger than your theories. But you still get to glimpse it, still get to map its structures, still get to wonder what lies past the edge. And sometimes wondering is enough. Step past the cosmic horizon in your imagination, and you are no longer in a universe of stars and galaxies. You are in a universe that is still too young to have any of those things. Here, light is not the clean, transparent messenger that carries information across billions of years. Instead, it is trapped, bouncing endlessly between charged particles like an impatient child in a crowded hallway. The era we are drifting into is known as the plasma epoch, and it lasted for hundreds of thousands of years after the Big Bang. During this time, temperatures were so high that atoms could not exist. Electrons and protons were constantly colliding and separating, preventing light from traveling freely. The entire cosmos was, in effect, glowing but opaque, like staring at the surface of the sun. The light you now detect as the cosmic microwave background is the fossil of this period, frozen in place at the moment when the universe cooled just enough for protons and electrons to combine into hydrogen atoms, allowing photons to finally slip free. This event is called recombination, though the name is misleading because it was actually the first time electrons and protons had successfully combined at all. Before that, photons existed but were constantly scattered, unable to move more than a few centimeters before bouncing off something else. After recombination, the fog lifted and the universe became transparent. That transparency has lasted ever since, a window into everything that followed. If you try to picture what the cosmos looked like during this time, it is both alien and strangely familiar. The whole universe was filled with a hot, glowing plasma, smooth to the eye, but with tiny density fluctuations, slightly denser patches where gravity would later tug more strongly, and slightly emptier patches where matter would thin out. Those denser patches are where galaxies would eventually form, like seeds sprouting in the soil of space-time. Without those faint differences, the universe might have expanded into a bland, featureless cloud, sterile and uneventful. It is only because of those wrinkles that you exist. You are, in a sense, a highly complex descendant of ancient lumps in plasma density. Not the most flattering family tree, but accurate. Now let's rewind the clock even farther into an era before recombination, before plasma, before anything resembling the world we know. The universe then was hotter, denser, and younger. At around 1 second old, it was a boiling soup of protons, neutrons, electrons, neutrinos, and photons, all colliding in a chaotic mess. This era is when the first light nuclei were forged in a process called Big Bang nucleosynthesis. Hydrogen and helium formed in abundance, with traces of lithium. These elements would later serve as the building blocks of stars, which would fuse them into heavier ones, eventually producing carbon, oxygen, iron, and all the other elements that make up planets and life. In that sense, your bones, your blood, even the device you are listening on, all trace their ancestry to those first few minutes of nucleosynthesis. Go back farther still, into the first fractions of a second, and things become even stranger. At around 10 to 36 seconds after the Big Bang, cosmologists think the universe underwent a period of rapid expansion called inflation. In this brief instant, space itself expanded exponentially, growing faster than the speed of light. Before you imagine this as a violation of physics, remember that nothing can move through space faster than light, but space itself can expand as quickly as it likes. Inflation stretched quantum fluctuations, microscopic jitters in energy, into macroscopic ripples, which later became the seeds of galaxies, clusters, and filaments. Without inflation, the universe would look very different, perhaps even chaotic and inhospitable to the kind of structure we depend on. Inflation also explains why the universe looks so uniform on large scales. If you glance around, galaxies are spread evenly in every direction, and the cosmic microwave background has nearly the same temperature no matter where you look. Without inflation, regions of the universe would not have had time to talk to each other and even out their temperatures. With inflation, they were once close enough to interact, then blown apart into regions now separated by tens of billions of light years. The smoothness of the sky is a silent clue that the early universe expanded unimaginably fast. Try to picture what that would look like. At first, the universe was smaller than a proton. Then in an instant, it ballooned into something macroscopic, a patch large enough to encompass everything we see today. Imagine blowing up a speck of dust until it was larger than a galaxy, and you still wouldn't capture the sheer absurdity of inflation. And yet, the evidence is written in the microwave background, in those faint ripples measured by satellites like COBE, WMAP, and Planck. These ripples are the fingerprints of inflation, patterns left behind by a process we cannot see directly, but can infer from the light that has traveled to us for nearly 14 billion years. Now step back into the tiniest fractions of time, earlier than inflation, and the truth is we enter the domain of speculation. The so-called Planck era, before 10⁻43 seconds after the Big Bang, is where our physics breaks down. General relativity and quantum mechanics both apply, but they do not yet agree. To describe this moment, we would need a theory of quantum gravity, something scientists have been chasing for decades. String theory, loop quantum gravity, causal dynamical triangulations. These are attempts to reconcile the laws of the very large with the laws of the very small. None are proven, all are tantalizing, and until one succeeds, the first instant of the universe will remain hidden behind a curtain we cannot pull aside. And yet the human mind insists on asking, what caused the Big Bang? Was it the beginning of time itself, or the result of something earlier? Some theories suggest a prior universe collapsed into this one, a cycle of bangs and crunches repeating forever. Others suggest that universes constantly bubble into existence within a wider multiverse, with ours simply being one of countless others that formed, inflated, and cooled. Still others propose that time itself may be emergent, that asking what came before the Big Bang is like asking what is north of the North Pole. It is not a meaningful question. Each possibility is strange, each stretches imagination, and each reminds us that our understanding is still partial, still incomplete. Now let's slow the pace and imagine what you would see if you could actually drift into these eras. At 1 second after the Big Bang, the universe would be a glowing fireball, temperatures at 10 billion degrees, filled with neutrinos escaping freely into space. At 1 minute, protons and neutrons would be fusing into helium, releasing energy in bursts across the plasma. At 380,000 years, the fog would lift as atoms formed, and the first photons would streak out, carrying the imprint of their birthplace. And over billions of years, those photons would stretch with the expansion of space, their wavelengths elongating until today they appear as the cosmic microwave background. What you see on the horizon is not just faint light, it is the memory of an entire universe transforming from chaos into order. This is the deepest you can travel in time using light. Farther back than the microwave background, and the universe is opaque. We can only infer its behavior with theory and equations, not direct observation. Yet those equations are remarkably powerful. They let us predict the abundance of elements, the distribution of galaxies, the geometry of space. And so far, observations have confirmed those predictions again and again. The universe has been generous in letting us test our guesses, even if it withholds its earliest secrets. There is one more humbling thought here. The observable universe contains maybe 2 trillion galaxies, each with billions of stars. And yet all of that structure, all of that richness, was seeded by tiny fluctuations in density, quantum ripples stretched by inflation into cosmic blueprints. Everything, galaxies, planets, life, even you, exists because of random jitters in energy fields nearly 14 billion years ago. You are the descendant of fluctuations, the product of chance magnified by expansion, proof that from the smallest uncertainties can grow the greatest complexities. So as you hover at this horizon, looking into the afterglow of the Big Bang, you are not seeing emptiness or darkness. You are seeing the most detailed history book ever written, one that begins with plasma and ends with you wondering about it all. The edge of the universe is not a finish line, but a time machine. It lets you look backward across 13.8 billion years and see the moment when light was freed. It lets you trace the story of atoms, stars, and galaxies back to the faintest wrinkles in temperature. And it lets you ask with both awe and humor how a cosmos that began as hot hydrogen soup managed to cook up things like pizza, cats, and philosophy lectures that run too long. And from here, the only direction left is even farther back, deeper into the speculative beginnings, where physics falters and imagination steps in. The Planck epoch, the inflationary instant, the mystery of origins themselves, that is where we drift next. You cannot go farther back in time with light because the cosmos before recombination is opaque, but you can go farther back with theory. And this is where the adventure shifts from what we can see to what we can infer. When you step through the wall of the cosmic microwave background, you enter a universe less than 380,000 years old, so hot and dense that matter and radiation are inseparable. It is not a place of stars or galaxies or even atoms. It is a sea of plasma, glowing everywhere, scattering light so effectively that no photon can travel more than the smallest fraction of a millimeter before being bounced aside again. If you could open your eyes in that place, you would see nothing in any direction, only blinding brightness in every corner of vision. It would be like standing inside the heart of a star, except there is no star, only everything. At about 1 second after the Big Bang, the universe is a furious soup. Temperatures are around 10 billion degrees, far hotter than the cores of even the most massive stars today. In this chaos, neutrinos decouple and stream freely into space. Their faint traces still detectable today as the cosmic neutrino background, though you have no chance of ever actually seeing it without instruments so sensitive they might as well be wizardry. Neutrinos are the ultimate cosmic introverts, slipping through matter as if it is not there at all. Even now, billions pass through your body every second, and you will never notice a single one. A few minutes later, when the universe is still only about 10 minutes old, conditions are just right for nuclear fusion on a universal scale. This period is called Big Bang nucleosynthesis. Protons and neutrons slam together to form the first nuclei of helium, along with traces of deuterium, lithium, and beryllium. Heavier elements are impossible at this stage because the universe expands and cools too quickly, shutting down fusion before it can continue. About 75% of the universe's ordinary matter becomes hydrogen, about 25% helium, and just a sprinkle of everything else. Those ratios are still with us today and match the predictions of cosmological models almost uncannily well. Every atom of helium in your lungs, every molecule of lithium in a smartphone battery was forged in those first few minutes when the universe itself was a reactor. Now rewind even further. Go back to fractions of a second after the Big Bang, and you leave the era of nucleosynthesis and enter an epoch where fundamental forces themselves behave differently. At around 10^12 seconds, the electroweak force splits into the electromagnetic and weak nuclear forces we know today. Before that, they were unified, indistinguishable parts of one interaction. Go earlier still, back to 10^36 seconds, and theory suggests all the forces we know except gravity were unified into one. And if you keep pushing back to the Planck time, 10^43 seconds, even gravity might merge into that unity. That is the holy grail of physics, the point where all forces are one, where a single mathematical description could in principle explain the birth of everything. We don't have that description yet, but we know it must exist, because physics cannot simply break down at the beginning and call it a day. It is during this early sliver, just after the Planck epoch, that inflation occurs. And inflation is one of those ideas that sounds like science fiction, but is actually one of the most successful theories in modern cosmology. In less than a trillionth of a second, the universe expands by a factor so enormous it is effectively impossible to visualize. A region smaller than a proton balloons into something larger than the entire observable universe today. It is not an explosion of matter into empty space. It is the stretching of space itself, pulling everything apart faster than light could travel, flattening the geometry, ironing out irregularities, and leaving behind a cosmos that looks smooth. But inflation does something else too. It takes the tiniest quantum fluctuations, random jitters of energy fields, and magnifies them to cosmic proportions. These fluctuations become the seeds of density differences, slightly denser here, slightly emptier there, that later grow into galaxies and clusters under the pull of gravity. Without inflation, you would not have structure, you would not have stars or planets or people. You would have a universe that was either completely uniform or hopelessly chaotic. The balance struck by inflation is both improbable and essential. Out of the quantum froth came the blueprint for everything. And if you think about that for too long, you realize something almost comical. You are here, listening to this, because of random, microscopic jitters in a quantum field nearly 14 billion years ago. Entire civilizations, histories, and species exist because the early universe had a case of nervous fidgeting. It is both absurd and profound at the same time. Now, what lies even deeper than inflation? No one knows. Some theories say inflation may never fully end. It might continue forever in some regions, spawning bubble universes endlessly, each with different properties, different physical constants, maybe even different dimensions. Our universe would then be just one bubble in an infinite froth, one pocket where inflation slowed and cooled enough to allow stars, galaxies, and life. Other pockets may collapse instantly or expand so rapidly that nothing interesting ever forms. The multiverse is not proven, but it lingers as a possibility because mathematically, inflation tends to produce it whether we like it or not. The irony of the universe is that you set out searching for its edge and discover it may be nothing more than one bubble in an endless foam, and then you realize you might not even be in the most interesting bubble, which, if true, is humbling in ways that are both painful and hilarious. But leave that aside for now and focus on the observable consequences. Even if the multiverse is real, we cannot see outside our own bubble, so what we have is this. A cosmos that began in fire, expanded in frenzy, and cooled into transparency, leaving behind a faint microwave glow across the entire sky. From that glow, we can trace the story forward. Matter clumped under gravity, stars lit, galaxies formed, heavy elements brewed, planets emerged, life appeared, and eventually some curious primates looked up and asked where the edge was. Standing at this horizon, you realize you are caught between two infinities. On one side, the infinite smallness of the Planck epoch, where time intervals are so brief that even the speed of light cannot cross the tiniest distance before the universe changes completely. On the other side, the infinite vastness of the cosmos beyond the horizon, stretching into regions we cannot see and may never know. You are a creature that lives in the middle, bound by seconds and meters, but you are asking questions about trillions of years and billions of light years. That mismatch is both your limitation and your strength. You cannot see the whole, but you can imagine it. And this is where the humor of the situation hits you. Human beings evolved to throw rocks accurately, to tell each other stories around fires, to worry about whether the harvest would come in on time. Yet those same brains, those same bundles of neurons, are trying to comprehend quantum fields and inflationary epochs. It is a bit like a goldfish trying to write a symphony. And yet, against all odds, the goldfish is humming Beethoven in its little bowl. You should take pride in that, even if the universe will never notice. So here you hover, having stepped beyond galaxies, beyond stars, beyond atoms and nuclei, into an epoch where space itself inflated like a balloon. You have traveled backward in time nearly to the beginning, and you are still standing, or at least imagining yourself standing, at the edge of knowledge. Beyond this, speculation multiplies, but the one certainty is this: you are part of a cosmos that began in simplicity and grew into complexity, and that complexity now includes you wondering about it all. And if there is one thing the universe seems to reward, it is curiosity. Because curiosity is the only tool you have that can stretch farther than light, farther than gravity, farther than inflation. It is the one thing that can cross horizons without breaking. And so, the journey continues, deeper into the first instance, deeper into the possibility of what might lie before beginnings, deeper into the questions that will not let go. So here you hover, having stepped beyond galaxies, beyond stars, beyond atoms and nuclei, into an epoch where space itself inflated like a balloon. You have traveled backward in time, nearly to the beginning, and you are still standing, or at least imagining yourself standing, at the edge of knowledge. Beyond this, speculation multiplies, but the one certainty is this: you are part of a cosmos that began in simplicity and grew into complexity. And that complexity now includes you wondering about it all. And if there is one thing the universe seems to reward, it is curiosity. Because curiosity is the only tool you have that can stretch farther than light, farther than gravity, farther than inflation. It is the one thing that can cross horizons without breaking. And so, the journey continues. Deeper into the first instance, deeper into the possibility of what might lie before beginnings, deeper into the questions that will not let go. To go deeper than inflation means stepping into the very first instant of the cosmos, into what physicists call the Planck epoch. This is the moment between time zero and about 10 to 43 seconds, known as the Planck time. It is unimaginably brief, so short that if you tried to compare it to a single second, you could fit more Planck times inside that second than there are seconds in the age of the universe. This is the boundary where all of our physics begins to collapse under its own ambition. During this epoch, the universe was so dense and so hot that all four of the fundamental forces may have been unified. Gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, behaving not as separate interactions but as one single force, a kind of primordial everything interaction. We do not have the mathematics to describe it properly yet. General relativity, which governs the very large, and quantum mechanics, which governs the very small, refuse to cooperate. You can almost picture them sitting at opposite ends of a cosmic dinner table, arms folded, glaring at one another. The equations of relativity curve space-time beautifully, predicting black holes and expanding universes, while quantum mechanics shrugs and throws dice, insisting everything is probabilistic and jittery. Put them together at the Planck scale, and the math produces infinities so nonsensical it's as if the universe itself is laughing at us. This is why physicists search for a theory of quantum gravity, something that can bridge these two frameworks into one description that works everywhere, from galaxies to quarks, from black holes to the Big Bang. Candidate ideas include string theory, which imagines the fundamental building blocks of reality, not as particles but as tiny vibrating strings, each vibration a different note corresponding to a different particle. Or loop quantum gravity, which proposes that space-time itself is quantized, made up of discrete loops, like a woven fabric of geometry at the smallest scale. These are elegant, fascinating, and wildly complicated theories. But so far they remain untested because the energies required to probe them are so high They make our most powerful particle accelerators look like toys. The Large Hadron Collider is impressive, but compared to the Planck scale, it is like trying to study ants with a magnifying glass when you really need a telescope the size of the solar system. What is certain is that the Planck epoch was dominated by quantum fluctuations of space-time itself. At that scale, even the fabric of reality is restless, bubbling with energy, curves and twists forming and vanishing in tiny instants. Space and time are not smooth and continuous here. They are grainy, foamy, flickering. This quantum foam is the playground of the early universe, and from it, inflation emerged, stretching those fluctuations into the scaffolding for galaxies and stars. And here is the frustrating, fascinating truth. Beyond the Planck epoch, we simply do not know. Time itself may not even make sense before this point. Some theories suggest the Big Bang was the true beginning, the first moment when time and space came into being. In that view, asking what came before is like asking what lies north of the North Pole. It is a category error, a question that assumes something where nothing exists. But other theories disagree. Some propose that the universe may be cyclical, endlessly reborn in a series of bangs and crunches, expanding, collapsing, and re-expanding forever. Others imagine a big bounce, where a previous collapsing universe rebounded into ours. Still others invoke the multiverse, suggesting that universes constantly bubble into existence from a larger inflating space, each one with its own arrow of time, its own beginning and end. None of these possibilities can be observed directly, but they can be reasoned toward. If our universe is cyclic, there may be imprints in the microwave background, faint echoes of previous cycles. If it is part of a multiverse, perhaps collisions between bubble universes could leave scars in the sky. So far, the evidence is ambiguous. The cosmic microwave background is astonishingly smooth, but whether it hides clues to a pre-Big Bang reality remains uncertain. It is like staring at a faded photograph, trying to see whether there is a ghostly figure in the background, knowing it might just be a smudge on the lens. And yet the question persists. Did time exist before the Big Bang, or did it begin with it? If time had no beginning, then the universe stretches back infinitely, and the Big Bang is simply the most recent chapter in an eternal story. If time began with the bang, then everything, every star, every life, every thought fits into a single bounded interval, finite but vast. Both options are unsettling in their own way. Infinity is overwhelming, but a hard beginning raises the even harder question of why it happened at all. Some physicists take a pragmatic approach. They say the question of before may not be scientifically meaningful if no observation can ever confirm it. That doesn't stop people from speculating, of course. Humans are not built to resist what if. So the debates continue, with chalkboards full of equations and conference halls full of arguments that usually end with someone muttering, "Well, maybe," and everyone nodding in exhausted agreement. From your vantage point, hovering at the edge of knowable physics, you see the paradox clearly. You have traveled backward across billions of years of cosmic history, past the birth of stars, the glow of the microwave background, the heat of the plasma, the first seconds of nucleosynthesis, the fleeting instants of inflation. And here you stand at the Planck wall, staring into a fog of speculation. Beyond it, either nothing or everything. And the fact that you cannot decide which is both maddening and exhilarating. And here is where humor sneaks back in. You realize the universe is under no obligation to make sense to you. It is not trying to be poetic or consistent or polite. It simply is. Your brain, evolved to worry about food and shelter, is now trying to pass the physics of space-time at 10:43 seconds. It is an almost comical mismatch, yet somehow you are making progress, building models, testing predictions, inching closer to answers. If the cosmos is laughing, it might also be impressed that you even got this far. So this is the frontier. The Planck epoch, the realm where physics falters and imagination runs free. It is the deepest you can travel, the most ancient moment science can even begin to describe. Beyond it lies the uncharted, perhaps the unknowable. And yet the journey has value, because in chasing the beginning, you discover meaning in the middle. The very act of asking is part of what makes you alive in a universe that would otherwise be silent. And with that, we pause. At the edge of the beginning, looking into the foamy chaos of space-time, wondering what, if anything, came before. The horizon of the past stretches no farther, and the only way forward now is back out. Back into the growing cosmos, back toward galaxies and stars and the long arc of cosmic evolution. Because the story of the universe is not only about where it began, but about where it is going. From the Planck epoch, you can go no farther back, at least not with the tools of physics as they exist today. The wall of speculation looms solid, a frontier of mathematics and imagination, where our knowledge stops. So now, instead of continuing backward, let us turn and drift forward, out of the haze of beginnings, through the stars and galaxies, and into the open question of what lies ahead. Because if one edge of the universe is its mysterious past, the other edge is its future, and the road toward that edge is being paved right now in the quiet expansion of space itself. Ever since the first seconds after the Big Bang, the universe has been stretching. Galaxies are not flying through space like sparks from a firework, but rather space itself is expanding, carrying galaxies along for the ride. This is not an easy thing to visualize, which is why cosmologists reach for metaphors like balloons with dots drawn on them. Imagine inflating such a balloon. The dots represent galaxies, and as the balloon expands, every dot moves away from every other dot. No dot is at the center, and no dot is doing the moving. It is the surface of the balloon itself that grows. Likewise, in the universe, it is space itself that stretches, and the galaxies are simply passengers. Edwin Hubble discovered this in the 1920s when he noticed that the light from distant galaxies was redshifted, stretched to longer wavelengths. The farther away the galaxy, the greater the redshift, meaning the faster it appeared to be receding. This observation was the first evidence that the universe was expanding. Decades later, the discovery of the cosmic microwave background confirmed it. The universe was not static, as Einstein once hoped it would be, but dynamic, evolving, restless. And here comes the twist, because the story of expansion is stranger than anyone expected. For most of the 20th century, astronomers assumed that gravity would gradually slow the expansion down. Perhaps it might slow enough to halt and reverse, leading to a big crunch where the universe collapses back into itself. Or perhaps it might slow but never quite stop, leaving the cosmos to drift outward forever, growing cold and thin. Either way, the future would be shaped by gravity tugging on matter. But in the 1990s, two teams of astronomers studying distant supernovae discovered something startling. Instead of slowing, the expansion of the universe was accelerating. Galaxies were not only drifting apart, they were doing so faster and faster over time. To explain this, cosmologists invoked a mysterious component of the universe called dark energy, an unknown form of energy permeating space itself, pushing galaxies apart. Dark energy does not clump or cluster like matter. It acts uniformly, as though space has an intrinsic pressure that resists being pulled together. We do not know what dark energy is. It could be the cosmological constant, a fixed energy density of empty space. It could be something dynamic, like a new field slowly evolving. Or it could be a sign that our understanding of gravity itself is incomplete. But whatever it is, it dominates the universe today. Roughly 70% of the cosmic energy budget is dark energy, 25% is dark matter, and less than 5% is the ordinary matter that makes up stars, planets, and you. Imagine being told that almost everything in existence is invisible and unknown, and the small fraction we can see just happens to be what we're made of. It is both insulting and comforting. Insulting because we barely matter, comforting because at least we know we matter to ourselves. So what does this accelerating expansion mean for the future? It depends on the nature of dark energy. If it is a cosmological constant, the expansion will continue forever, faster and faster, pushing galaxies beyond our horizon until only the local group remains bound. Hundreds of billions of years from now, future observers, if any exist, will see nothing beyond their local cluster. The rest of the universe will have faded beyond visibility, leaving them in apparent solitude, unaware that galaxies ever existed beyond their own. A cosmic loneliness imposed by expansion. If dark energy grows stronger with time, the result could be even more dramatic. In a scenario called the Big Rip, space expands so violently that galaxies, stars, planets, and eventually even atoms are torn apart. The expansion accelerates without limit, shredding reality itself. If dark energy weakens, on the other hand, gravity might one day take over again, halting expansion and reversing it. The universe would collapse in a fiery big crunch, possibly bouncing into another cycle. And if dark energy is something even stranger, then futures we cannot yet imagine may unfold. Perhaps expansion will asymptotically slow to a steady drift. Perhaps it will oscillate in waves. Perhaps it will dissolve space-time into something new altogether. Cosmologists write equations, run simulations, debate in conferences, and drink too much coffee, but the truth is we still do not know. Let's play these futures out one by one, just to appreciate the range. In the eternal expansion scenario, galaxies move beyond the observable horizon one after another. First the distant ones, then the nearer ones, until only the gravitationally bound companions remain. The night sky grows emptier over billions of years. Stars continue to burn, but eventually even they exhaust their fuel. White dwarfs fade into black dwarfs, neutron stars cool into silence, black holes evaporate through Hawking radiation. Trillions of years into the future, the universe becomes dark and cold, a lonely sea of faint remnants. This is called heat death, not because it is hot, but because energy is evenly distributed, leaving no gradients to power structure or life. A flat, featureless cosmos at thermodynamic equilibrium. It is the most boring apocalypse imaginable, the cosmic equivalent of everything in the fridge being room temperature forever. In the Big Rip scenario, things end with more drama. As expansion accelerates, clusters are torn apart, galaxies fly apart, solar systems disintegrate. When the expansion rate surpasses the binding energy of planets, Earth itself is pulled from orbit, the moon drifts away, and eventually even the atoms of matter are ripped asunder. Space itself stretches beyond the capacity of forces to hold things together. It is a chaotic, violent, absurd end, like the universe playing a prank too big for anyone to survive. In the Big Crunch scenario, gravity wins, expansion halts and reverses, galaxies fall toward one another, clusters collapse, temperatures rise. Stars reignite as gas is compressed, black holes merge into larger black holes, until finally everything collapses into a singularity, not unlike the one we think began it all. Perhaps from that singularity, a new universe is born, a cosmic phoenix rising again, continuing an eternal cycle. If so, this might not be the first universe nor the last, just one in a chain stretching endlessly backward and forward. A comforting thought if you like recycling, a terrifying one if you wanted your universe to be unique. And then there is the wildcard scenario, the unknown, because dark energy could be none of the above. It could shift, change, decay into something else entirely. The future of the cosmos could surprise us in ways no one has predicted. And the one constant in cosmology is that the universe rarely behaves exactly as you expect. Remember, not long ago we thought expansion should slow, not accelerate. But here is the part that matters for you, here and now. These fates unfold over timescales so vast, they make the age of the universe today, 13.8 billion years, look like a coffee break. Human concerns about years, decades, or even millennia are laughably tiny next to trillions of years. On those scales, civilizations rise and fall in less than the blink of a cosmic eye. You will not be around for heat death, the Big Rip, or the next Big Bang. Yet asking about them still matters, because the act of asking connects you to the whole story. You are not simply a passenger in a galaxy on its way to an unknown future. You are a witness, and that alone gives your existence a kind of cosmic weight. So as you drift farther into this accelerating universe, you feel both small and strange. Small because you are a fleeting creature in a vast cosmos dominated by forces you cannot control or even fully explain. Strange because despite that, you can trace the arc of time from the first seconds after the Big Bang to trillions of years into the future. You can stand at both edges of the universe in thought, the past and the future, and hold them together in one mind. That is the kind of trick no other creature we know of has ever pulled. And maybe that, more than survival or reproduction or comfort, is what makes you remarkable. And the journey is not over. Because now that we have traced the possible futures of expansion, we can ask another question. Not just how the universe will end, but how it looks as it evolves along the way. The cosmos today is not the cosmos of tomorrow, and as we push forward, we step into the far future, a realm of fading starlight, dying galaxies, and physics stretched to its limits. The present-day universe looks vibrant, at least by cosmic standards. Galaxies spin, stars blaze, nebulae glow, and planets orbit in the quiet company of their suns. But the universe, like any story, has chapters, and we live in what might be called the stellar era, the age when stars exist and light fills the sky. This chapter will not last forever. Already the balance is shifting as expansion carries galaxies away and dark energy dominates the cosmic stage. If you want to know what lies at the far edge of time, you have to imagine a universe stripped piece by piece of its familiar features until only the strangest remnants remain. Let's start small with stars themselves. Our sun is about halfway through its life, with roughly 5 billion years of fuel left. When its core hydrogen runs out, it will swell into a red giant, its outer layers expanding past the orbit of Earth, which is bad news for Earth. Eventually, it will shed those layers into space as a planetary nebula, leaving behind a white dwarf, a dense remnant roughly the size of Earth, but with half the sun's mass, glowing faintly as it cools. Other stars will follow similar fates, though the more massive ones will end more violently, collapsing into neutron stars or black holes. For the next 100 trillion years or so, stars will continue to form, live, and die. That might sound like plenty of time, but remember, the universe is already 13.8 billion years old, so 100 trillion is an absurd extension of the timeline. Stars forming now will shine for billions of years before going dark, but eventually the supply of gas that fuels star formation will run out. Galaxies will stop producing new stars. The existing stars will burn out one by one, leaving behind only the remnants, white dwarfs, neutron stars, and black holes. Astronomers call this the end of the stellar era, and it marks the beginning of a long twilight. White dwarfs will cool into black dwarfs, hypothetical objects that no longer shine, radiating only faint heat. Neutron stars will remain as ultra-dense corpses, cities of matter crushed into atomic nuclei. Black holes will dominate, swallowing whatever matter remains within their reach. The universe will no longer be filled with blazing suns, but with faint embers, a graveyard of remnants drifting through expanding space. Now extend the timeline even further. Trillions of years pass. The last stars flicker out. Planets drift frozen and dark around extinct suns. Some are ejected from their systems entirely, wandering interstellar space alone. Galaxies themselves become ghostly, filled not with stars, but with stellar corpses and black holes circling like predators. Light grows scarce, and the universe slips into a state astronomers call the degenerate era. But physics continues to tick away, and even these remnants are not eternal. White dwarfs may eventually undergo proton decay if protons are not stable. This is still uncertain, but if protons do decay, then even the matter of white dwarfs and neutron stars will slowly dissolve into radiation. If protons are stable, then black dwarfs will simply persist, faint and inert, for unimaginably long timescales. Either way, the grand majority of the matter you see today will not remain in recognizable form. And then, looming above all of this, are black holes. They will be the monarchs of the far future, swallowing stars, planets, gas, and even each other. Over time, galaxies may collapse into central black holes, merging again and again into titans with billions of solar masses. These giants will dominate their neighborhoods for eons, but even black holes are not eternal. Stephen Hawking showed that they radiate faintly, a process known as Hawking radiation, caused by quantum effects near the event horizon. For stellar mass black holes, this radiation is negligible, but over trillions upon trillions of years it adds up. Picture this: 10 to the power of 100 years into the future. That's a 1 followed by 100 zeros. Every black hole will have evaporated. The universe will no longer contain galaxies, stars, or planets. Only a thin mist of elementary particles and low-energy radiation spread across an expanding void. This is the so-called heat death, the era when the universe reaches maximum entropy. No gradients remain, no energy differences to fuel motion or life. It is a cosmic equilibrium, utterly silent, utterly dark. Now, if you're still following this and not asleep, you might be thinking this sounds bleak. And yes, it is bleak, but it is also fascinating, because it means you live in a golden age, the luminous chapter of cosmic history. When stars exist, galaxies shine, and skies are filled with light. If you were to pick a time in the universe to be alive, now is one of the best. Go too early, and the universe is an opaque plasma with no stars. Go too late, and it is a graveyard of black dwarfs and evaporating black holes. By cosmic luck, you live in the brief interval when the night sky is dazzling. Call it cosmic prime time. And the humor here is not lost. Imagine future civilizations, trillions of years from now, trying to do astronomy. They would see only their local galaxy cluster, because everything else would have slipped beyond their horizon. They would think the universe is small, static, and empty. They might not even suspect the cosmos once contained billions of galaxies glowing with stars. They would be wrong, but they would have no way to know it. You, by contrast, can see the grand design of the cosmic web, the expansion, the microwave background, the past and possible futures. You live in a privileged age of knowledge, though you rarely think of it that way when stuck in traffic. But let's not leave it on too bleak a note, because physics may yet surprise us. Dark energy could shift, change, or decay into something else entirely. The arrow of time might reveal a hidden symmetry. New physics could appear at extreme scales, rewriting the script of the deep future. Maybe heat death is not the end, but a transition to something we cannot yet imagine. Perhaps new universes will bud off from black hole singularities, carrying with them new sets of laws, new stories to unfold. In that case, what looks like an ending from your perspective might simply be a beginning in disguise. So you stand here, not at the literal end, but at the edge of foresight, a horizon of time rather than space. Behind you stretches a history written in stars and galaxies. Ahead of you stretches a future of darkness and silence, unless something unforeseen intervenes. Between them is now a fragile sliver when the universe is full of light and complexity. A sliver that contains you, listening, wondering, imagining. And that is where the paradox lives. You are tiny, brief, fragile, but you carry the ability to imagine not only billions of years past, but trillions of years forward. You are a creature of the present who cannot resist thinking about both edges of time. And maybe that is the most remarkable fact of all. By now, the universe has grown unimaginably old. Stars have burned their fuel, galaxies have grown dim, and the last black holes are quietly evaporating into faint trickles of radiation. What remains is not the vibrant cosmos you know, but a cold, thin mist of particles spread across an ever-expanding void. This is the so-called dark era, the chapter of cosmic history when entropy is nearly at its maximum and nothing large or structured remains. And yet, even in this apparent silence, physics continues to whisper. Entropy is the key to this future. It is often described as disorder, but that is not quite right. Entropy is about the number of ways a system can be arranged without changing its overall energy. High entropy means there are many possible arrangements. Low entropy means there are few. The early universe, despite being hot and energetic, was actually low entropy because it was smooth and uniform. Over time, as gravity pulled matter into stars, galaxies, and black holes, entropy increased. Now, with everything dissolved into particles and radiation, entropy is near its peak. In a sense, the universe has run downhill into equilibrium, and once there, no new structures can spontaneously arise. It is like water settling into the lowest point of a basin. Once it is there is nowhere left to flow. But the details of this equilibrium are strange. Even in a heat-death universe, particles still exist. Photons, neutrinos, perhaps some exotic remnants. They move through space endlessly, rarely interacting because everything is so dilute. A photon might travel a trillion light years before colliding with anything else, which is to say it will never collide at all. Space-time itself is still expanding, pushing particles farther apart, so the likelihood of interaction dwindles towards zero. The cosmos becomes effectively static, not because nothing exists, but because nothing meaningful happens anymore. Of course, this raises the obvious question: is that truly the end, or just the end as you currently define it? Physics thrives on loopholes, and one possibility is that even in a heat-death state, rare fluctuations could occur: thermal fluctuations, quantum fluctuations, or something stranger. In principle, given infinite time, any arrangement of particles could spontaneously form again, including, hypothetically, stars, galaxies, or even conscious beings. This leads to the bizarre concept of Boltzmann brains, self-aware observers that pop into existence out of random fluctuations in a high-entropy universe. The idea is unsettling because if the universe lasts forever, Boltzmann brains should vastly outnumber ordinary observers like you. And if that is the case, then statistically you should be one right now. Of course, this is absurd, and most cosmologists treat it as a sign that our understanding of entropy in the far future is incomplete. But it is the kind of absurdity that cosmology occasionally delivers, a reminder that the universe is not obligated to align with your sense of normalcy. Meanwhile, let's return to black holes, because they still shape this era. Long before heat death is complete, black holes dominate. The biggest ones, supermassive black holes at galactic centers, hold out the longest, while stellar mass black holes evaporate on timescales of about 10 to 67 years. The giants last vastly longer, up to 10 more 100 years or more. That is a 1 with 100 zeros. Eventually, even they radiate away through Hawking radiation, releasing their mass as faint showers of photons and particles. When the last one evaporates, the universe transitions fully into the dark era, with no structures left to organize matter. Yet the possibility remains that the laws of physics themselves may not be eternal. The stability of the proton, for example, is still an open question. If protons decay, then even the matter that makes up black dwarfs and neutron stars will eventually disintegrate into radiation. The half-life for proton decay, if it exists, is staggeringly long, greater than 10^34 years, but in the dark era, even that will eventually run its course. What is left then is pure radiation and stable particles like electrons and neutrinos spread thinly across expanding space, a universe emptied not by catastrophe, but by attrition. And yet the very concept of expansion cannot be taken for granted forever. Cosmologists are still uncertain about whether dark energy is truly constant. If it is, then space will continue to expand exponentially, galaxies will drift beyond visibility, and the universe will fade into eternal emptiness. But if dark energy evolves, decays, or changes sign, the story could shift dramatically. A change in the equation of state of dark energy could cause expansion to slow, halt, or even reverse, leading to a collapse, a big crunch rebirth into another fiery beginning, or in a more exotic twist, a shift in vacuum energy could trigger a false vacuum decay, a bubble of lower energy space expanding at the speed of light, rewriting the laws of physics inside it and annihilating everything we know. Not the friendliest of endings, but certainly dramatic. There is another question lurking here. What if time itself is not infinite? What if time has a kind of built-in expiration, like a book with a final page? You live assuming time is an endless line, stretching both backward and forward. But if the universe is finite in extent and finite in duration, then time itself might be bounded, a beginning, a middle, and an end. The thought is disturbing because it makes you wonder what it means to end time. Would reality simply stop? Would there be no after? Your brain, built to expect continuities, balks at the notion of a hard end. And yet cosmology does not rule it out. Now let's imagine you could actually drift into this far future. At first, you would see galaxies still visible but faint, redshifted farther and farther as expansion carries them away. Then, billions of years later, only your local cluster would remain. The rest would be gone, receding beyond the cosmic horizon. Then, even in your own galaxy, stars fade. One by one they wink out until only black dwarfs remain, faint cinders of their former brilliance. The night sky, once full of stars, becomes empty. Then black holes take over, silent rulers of dark galaxies. And finally, even they evaporate, leaving only a faint hiss of radiation. You look around and see nothing. No galaxies, no stars, no planets, only emptiness dotted with the occasional stray particle. And the strangest thing is not the emptiness itself, but the sheer scale of time it took to get there. The numbers are so large they defeat comprehension, as though time itself has become meaningless. But here is the philosophical twist. The universe does not owe you a happy ending. It is not a story written for your satisfaction. It is a physical system, obeying laws, playing out possibilities. And yet the fact that you can imagine all this, that you can trace the arc from the first microseconds after the Big Bang to trillions of years into the future, is remarkable. You are not simply a speck adrift in a meaningless void. You are a speck that can comprehend the void, that can chart its past and speculate on its future. That ability is itself a kind of cosmic defiance. And so, standing at this far edge of time, you see two horizons at once. Behind you, the microwave glow of the infant universe. Ahead of you, the thin radiation of a universe at heat death. Between them lies everything: stars, galaxies, planets, life, thought, curiosity. The arc of existence traced in light and gravity and entropy. You realize that the edge of the universe is not a single place or time, but many edges. Edges of sight, edges of knowledge, edges of time, edges of meaning. And you, improbably, have stood at each in turn. You have drifted across time in both directions now, past the horizon of galaxies into the infant universe, back to the Planck epoch where physics itself falters, and then forward again, past the death of stars, the rule of black holes, and the long silence of heat death. You have walked the line between beginnings and endings, between blazing light and infinite dark. And here, at the farthest edges of imagination, the question becomes not what lies beyond, but what it means for you to even ask. Think about the absurdity of it. You, a being who lives less than a century on a rocky planet circling an average star, have managed to map the history of the cosmos across 13.8 billion years into the past and trillions upon trillions of years into the future. You evolved not to solve cosmology but to survive, to find food, to avoid predators, to gossip about your neighbors. And yet here you are, pushing equations and telescopes to their limits, asking about edges so far removed from your daily reality that they may as well be myths. The irony is both humbling and hilarious. But perhaps that is the point. Perhaps the value of this journey is not in reaching an answer, but in stretching your mind beyond its ordinary boundaries. To look at the sky and realize it is not just decoration, not just pinpricks of light, but a map of the entire story. Stars that burned billions of years ago, galaxies billions of light years away, light that has traveled across most of time itself just to reach your eyes. Every glance upward is a conversation with the past, and every projection forward is a conversation with possibility. When you stood at the cosmic microwave background, you saw the afterglow of creation. You saw how tiny ripples in density became galaxies, how simple hydrogen became stars, how stars forged heavier elements, how those elements built planets and people. You realized that every atom in your body carries a history longer than the Earth itself. And when you drifted forward into the future, you saw how even galaxies and stars are temporary, how black holes will rule and then fade, how entropy will eventually quiet everything into stillness. You realized that your existence happens in a fragile window, a cosmic now filled with light that will one day be gone. And then you saw the paradox. You are small, but you are also vast in perspective. The universe is immense, but it is also finite in what you can observe. Knowledge is limited, but curiosity is limitless. You cannot see beyond the Planck epoch, yet you can imagine it. You cannot survive to witness heat death, yet you can describe it. You are a creature bounded by time, and yet your mind spans eternity in both directions. That is what it means to stand at the edges of the universe. Of course, the edges themselves are slippery things. The edge of space is not a wall but a horizon of light, the farthest distance photons have traveled since the Big Bang. The edge of time in the future is not a wall either, but the moment when entropy reaches its peak and nothing more can happen. The edge of knowledge is where mathematics breaks, where relativity and quantum mechanics refuse to agree, and the edge of meaning is where you stop asking how and begin asking why. Different edges, all connected, all inviting you to peer across. And maybe this is why the universe feels so strange to us. It does not fit neatly into categories. It is expanding but without a center. Finite in what we can see, but possibly infinite beyond. Simple in its ingredients, but complex in its outcomes. It is a system that produces galaxies and black holes, but also beings like you who can laugh at the absurdity of Boltzmann brains. The fact that the same laws that govern hydrogen and helium can also give rise to Shakespeare and jazz music is a kind of cosmic punchline, and you are part of it. What would you find if you truly reached the edge of the universe? The honest answer is probably nothing you could recognize. You would find limits, horizons, boundaries of vision and thought. You would find questions without answers and answers without certainty. You would find that the universe does not end cleanly but fades into regions of the unknown, like coastlines fading into fog. And yet, you would also find yourself, because the act of looking, of asking, is what draws the edge for you in the first place. Without observers, the edge has no meaning. With you, it becomes a story. And so here we close the circle. You began by asking what would happen if you kept going, past the stars, past the galaxies, past everything. You discovered that you cannot hit a wall, only horizons. You discovered that the past is written in light and the future in expansion. You discovered that the universe has no obligation to be comprehensible, but you comprehend it anyway, piece by piece, like a puzzle with missing corners. And perhaps most importantly, you discovered that wonder itself is endless. The edges of the universe are not just out there, they are within you, in the limits of your knowledge, in the scope of your imagination, in the questions that keep you awake at night. They are the edges of curiosity, the places where you lean forward and say, what if? And that may be the most profound thing of all. So the next time you step outside and look at the night sky, remember this journey. Remember that every star is a messenger from the past, every galaxy a story written in light, every silence a clue about the future. Remember that you live in the rare moment of cosmic history when the universe is ablaze with stars and full of information to read. And remember that even though you are tiny, your questions are vast. You can hold the edge of the universe in your mind, even if your feet never leave the ground. And with that, you let go. The edges recede, the horizons blur, the galaxies fade. What remains is the quiet, the vastness, and the strange satisfaction of knowing that the universe, however it began and however it ends, has been seen and wondered about by you. You have walked the arc of the cosmos now, backward to its fiery birth, forward to its silent future. You have seen stars form from hydrogen clouds, galaxies collide in slow motion, black holes swallow light, and the eventual spread of radiation into the great quiet. You have passed through the Planck epoch, where time itself stutters, and through the far future, where entropy rules everything. And yet, After all of this traveling, after imagining distances and times so absurd they melt language itself, you are left with one question that lingers heavier than the rest. What does it all mean to stand at the edge of the universe when you yourself are made of it? Because edges, when you really think about them, are illusions. The universe has no boundary like a fence or a wall. What you call an edge is simply the limit of what you can measure, what you can imagine, what light has had time to carry to you. Beyond it, things still exist, whether or not you will ever touch them. The same is true of time. You call heat death an ending, but that is only an ending from your perspective, a species that measures meaning in lifespans and stories. To the universe, there is no drama in fading into equilibrium. It is just another state of being, as ordinary as plasma was in the beginning. Think about it. The early universe was filled with heat and light, smooth and uniform, yet we do not mourn its lack of stars. We simply accept it as a phase. Why should the end of stars be any different? Perhaps the cold, quiet future is not tragedy, but transformation. Perhaps the cosmos cycles into new forms of order we cannot predict, patterns too slow or subtle for us to even define. The arrogance is assuming that we have the right frame of reference to declare what is meaningful on scales of 10 by 100 years, and yet you cannot help but humanize it. You look at galaxies vanishing beyond horizons and feel loss. You look at black holes evaporating and feel finality. You look at entropy and feel despair. But maybe that is projection. Maybe the universe is not dying at all. Maybe it is simply continuing, indifferent to whether the story pleases you. In that sense, the edge of the universe is a mirror. It shows you not just the cosmos, but your own need for beginnings and endings, your own hunger for narrative in a system that offers none. But here is the strange gift in that. Precisely because the universe does not hand you meaning, you are free to make it. You are free to declare that your century of life on a tiny planet is enough. Because in that century you can imagine billions of years backward and forward. You are free to say that a sliver of starlight caught in your eye on a clear night is proof that you are part of something that spans eternity. You are free to look at the absurd scale of everything and laugh because you manage to understand any of it at all. Consider how unlikely it is that you even exist to ask these questions. Hydrogen fused into heavier elements, stars lived and died. Carbon and oxygen scattered into space, planets formed, chemistry played its long game, and consciousness emerged. Out of all that, you arrived. You are the product of cosmic accidents stacked in a line billions of years long, and you have used your brief moment not only to survive, but to ask about the beginning and the end of the universe. That act alone is extraordinary. You are the universe becoming aware of itself, however briefly, however incompletely. And maybe that is the true edge, not the cosmic microwave background, not heat death, not the limits of observation or physics. The edge is awareness itself, the ability of matter to reflect on its own existence, the ability of stardust to say, I am here and I want to know why. The universe may not care, but you do, and that matters enough. So if you truly traveled to the edge of the universe, what would you find? You would not find a wall or a boundary or an answer carved in stone. You would find horizons, horizons of light, of knowledge, of imagination. You would find mystery stretching endlessly in both directions, daring you to ask more. And you would find yourself standing there, not with certainty, but with wonder, which is far more powerful. And that is where the journey ends. Not with finality, but with reflection. Not with a closed door, but with the realization that edges are where curiosity lives. You have traveled across the greatest distances thought can imagine, and in the end, you discovered that the most astonishing thing was not the galaxies, or the black holes, or the fading of stars. It was that you could take the trip at all, sitting still, with only your mind as the vessel. The edge of the universe is not out there waiting for you to arrive. It is wherever you choose to pause and look outward, asking the next impossible question. And when you do, the universe grows, not in size but in meaning. So now, breathe out slowly. Let the galaxies drift, let the horizons fade. Know that you have stood at every edge, past and future, and that you carry them with you always. The universe may one day fall silent, but your curiosity never has to.